This problem is related to conformation of alkane. So easy one. We have to draw the potential energy diagram. So conformation. So you see, this is something related to conformational analysis. So this says 2-methyl butane. So 2-methyl butane. So 1, 2, 3, 4. 2-methyl butane. Sighting along C2C3 bond, draw the Newman projection. So C2C3, so this is carbon 1, this is 2, this is 3, this is 4. So we have to draw the conformational analysis. We have to draw the different conformers along C2C3 bond. So we have to draw along C2C3 bond. So first part says draw the most stable conformer. So draw the most stable conformer in Newman projection form. So I can say, so let us say this is the front carbon. We have to look from C2C3. So this will become the front carbon. So on front carbon 2, we have one CH3, another CH3 and one H. So let us say one H, CH3, and then we have CH3. Now this is the back carbon. On the back carbon we have one CH3, one hydrogen, another hydrogen. So we will have basically two hydrogen and one CH3 on the back carbon. So let us first put any structure and then we will write. So this is two hydrogen and one CH3 on the back carbon. Now we need most stable. So most stable is possible only if these two CH3 groups are as apart as possible. So I can write something like this. So let us say this is bottom one. So let us keep the bottom one here, and the front carbon, so this is the back carbon. Okay, so let us put this front carbon. Okay, so let us rub this one. So I can put something like this. So let us keep the front carbon something like this, and back carbon, what I can do is this CH3 should be as opposite as possible. So let us put this CH3 here and then put 2H. I cannot basically make another structure that is more. This is the most stable structure even if I put CH3 here. So this is the most stable. You can try yourself. If you are writing something like this, hydrogen CH3 here on the bottom carbon, so this is the front carbon, you have CH3 H. On the bottom carbon you have writing CH3 somewhere here, H. You may be writing this formula. This is the same as, so this and this are basically same. You see CH3 and CH3 are anti to each other. One CH3 is Gauche to this CH3. Same thing here. Two CH3 is opposite. One is Gauche to this CH3. So this is the most stable conformer. What the part B says? Part B says draw the Newman projection of least stable. Oh my God, this is the least stable conformer. Basically this is the least stable, because in this case you have most hindrance, most steric hindrance, steric repulsion. No, this is the most stable. Okay, this is the most stable. No, repulsion is minimum in this case. So this is the most stable. We have to write down the least stable. So in the least stable you must have eclipse conformer. So put CH3 here, CH3 here, H here. Now you will have one CH3 must be here, another hydrogen here, another hydrogen here. So this is the least stable conformer. So you see, we can draw the structure from, this is the most stable. So you have seen right now, this is the most stable, CH3, and there you have a CH3H, hydrogen and hydrogen. So this is the most stable conformer 1. Now if I rotate this, so let us rotate the front carbon, keep as it is. Let us rotate the back carbon. If I rotate the back carbon by 60 degree, what I will get? So I will have front carbon as it is, CH3H, and back carbon, if rotated by 60 degree, this H comes here, this CH3 goes here, and this hydrogen goes here. If I even rotate to 60 degree more, what will happen? Now the back carbon is rotated, so in this way this rotation is. Now this back carbon, its hydrogen is here, it will come here. So keep the front carbon same. CH3, CH3H. This hydrogen will come here. This CH3 will go here. And this hydrogen will go here. So this is the, even if I rotate one more time by 60 degree, so I will get something like this. CH3, CH3H. Now this hydrogen goes here. This CH3 goes here. And this hydrogen goes here. Now let us call this compound 1, this is 2, this is 3, and this is 4. You see, compound 1 and compound 3 is same, because in this case CH3 is anti, CH3, no, 1 and 3 is not same, because CH3 in this case is not anti. Okay, so let us rotate one more time by 60 degree so that we can get the same. So if I rotate one more time by 60 degree, I can draw the structure. So front carbon remains as it is, CH3, CH3H. Now CH3, this comes here, so this CH3 here. Now this hydrogen goes here, this hydrogen goes here. Now this is the fifth one. Now we can say this fifth one and the first one is same. You see, this first one and fifth one is same, because in the first one this CH3 and this CH3 is anti. In the fifth one this CH3 and this CH3 is anti, and one CH3 is Gauche. So first and 5 are same. 1 and 5 are same. Similarly, you can see 2 is same as, I think 2 is same as 4, because CH3, CH3. So 2 and 4 are same. But 3 is different, and 3 is more stable. 3 is different. 3 is different a structure, and we know 3 is most stable. No, 3 is not most stable. So 1 is most stable and 5 is most stable. So this is 1 is most stable. So this is most stable. And now this one is the least stable. So 2 is the least stable. So question also says, have a qualitative idea or quantitative, because the bond synergy is given. So static repulsions are given. You have to draw the quantitative energy. It is given. So CH3 repulsion. So repulsion between one CH3 group is 11 kilojoule per mole. So this is given to you. Also given. So this is CH3 repulsion when they are eclipsing to each other. CH3 repulsion when they are Gauche to each other. This is given to you. This value is 3.8 kilojoule per mole. So this value is 3.8. So 3.8 kilojoule per mole. This is also per mole when they are Gauche to each other. You have been also given some more energy. CH3 a repulsion that is given. Now you will need hydrogen repulsion. Hydrogen repulsion energy is also given. So let me see where this is given. There is a table that is given in the table. So I have to see this value. So CH3H repulsion, when CH3 and H are eclipsing to each other, this repulsion energy is also given 6 kilojoule per mole when they are eclipsing to each other. You have been also given CH3H repulsion that is given. Hydrogen repulsion we will also need. If hydrogen are eclipsing to each other, the energy is 4 kilojoule per mole. So this is when they are eclipsing to each other. Now you see, we can basically calculate the energy in each cases. So let us calculate the energy for most stable conformer. In this case, two CH3 are basically eclipsing Gauche to each other. this CH3, this CH3, and let us assume these energies are very less. CH3, CH3 repulsion, HH repulsion, CH3, H repulsion, these are very less. Only consider CH3, CH3 Gauche repulsion is 3.8 kilojoule per mole. So this means this molecule will have energy of 3.8 kilojoule per mole because repulsion is 3.8 kilojoule. Now in this case, the molecule 2 will have CH3, CH3 repulsion, that is eclipsing, and this energy is 11. So we will have, so let me write here 11 plus CH3H repulsion. CH3H repulsion when they are eclipsing, that is 6. So I have to add plus 6 also. So this is 11 plus 6. Hydrogen repulsion is also given, that is 4 kilojoules. So I have to add plus 4 more. So this is 21 kilojoule per mole. So this is given for this molecule. Are you getting or not? Basically we are adding the repulsion. Now in this case you see CH3 repulsion when they are Gauche, this energy is 3.8. So 3.8 plus CH3CH repulsion is minimized. CH3 once again when they are Gauche, so that is 3.8. So this energy is 7.6 kilojoule per mole. So energy of this is 7.6 kilojoule per mole. Now we have calculated the energy for all because 1 and 5 are same, 2 and 4 are same, 3 is different. So we have calculated 1, 2, 3. So there are only 3 kind of, we can basically make a potential energy diagram. So potential energy diagram will something look like, so conformer 1, that is the highest, the lowest energy, 3.8 kilojoules. So let us say we have 3.8 somewhere here. So this is my 3.8 kilojoule line. Now the second, so this is the first conformer, that is 3.8. This is the most stable. Now the second conformer has an energy of 21 kilojoule when I rotate by 60 degree. So when rotation is 60 degree, so you see when rotation is 60 degree, this has energy of 21 kilojoule. So this value is 21 kilojoule per mole. Now this is a structure 2. Now if I see a structure 3, if I rotate by 60 degree more, now energy is only 7.6 kilojoule per mole. So 120, when the angle of rotation is 120 degree, this energy is 7.6. So this value will come somewhere here. So this is 7.6. So this is 3. So this point, and this point. Now if I go more, so 4 has the same energy. You see 4 has same energy as 2. So 4 has same energy as 2. We have already said. So 4 has same energy as 2. So you see 4 has same energy as 2 here. So I can put 2 once again. So when angle is 180 degree, so this is my 4. And 5 has same energy as 1. So 5 will be somewhere here. So when angle is 240 degree, 5 is somewhere here. Now if I join these lines, I will get something of this kind of plot. And now 6. Similarly you can draw the 6. What will be the structure of 6? And what will be the structure of 7? You can make a plot. You see basically you will be repeating the same graph after after 3, because 1, 2, 3 after the energy, the fourth is same as, so you have this graph. So this is the individual graph, and then you are repeating the same graph again and again. Are you getting or not? Not same. 3, 1, 2, 3, and now this is the 4 is same as same, that is the same as 2. Now this is same as this one. So you see you will get the same kind of graph if the periodic of this is the periodic one. So this is called conformational analysis. So important point in this case, you have to calculate the individual molecular energy if the each repulsion is given to you. If the repulsion is given like CH3 eclipsing repulsion, CH3H eclipsing repulsion, CH3 Gauche repulsion, if all these repulsions are given, you can basically calculate the potential energy, and then you can plot the diagram. So you see this energy is 3.8, this energy is 21, You see, this energy is 3.6, this energy is 21, and now this energy is 7.6. So this energy is 7.6, this energy is 21, and this energy is 3.8. You can plot these values. Okay. We'll discuss. Let us check this. If I rotate one more time by 60 degree, what happens? Let us check this one. In this case, am I getting the same thing or I'm getting different? If I rotate by 60 degree, the back carbon, we will have CS3, here I have H. Now this goes here, CS3, this goes here, that is H. Now this goes here. Now this molecule I have not got basically. Now what is the energy? This repulsion is 6. You see here, CS3, H repulsion is 6 kilojoule per mole. So 6, this is also 6, this is also 6. So this molecule will have 18 kilojoule per mole energy. So now we will get another molecule, one another conformation that has 18 kilojoule. So 18 will come somewhere, so at the angle of 300. So this will come 18, so this is somewhere here. So this is 6. If we want to do more, let us rotate one more time by 60 degree. So we will have, because conformational analysis you have to rotate till you get the same molecule. We have not done that. You can do this at your home. CS3, CS3H, this is the front carbon. If you rotate CS3, this H goes here, this goes here. Now this is same as, you see this is same as 1. So 7 is same as 1. So there is no point of rotating more. So 7 will have same energy. So now I am 100% sure this goes here, and after that this will come to the this 5 is 3, so this will come to the 1. So basically 5, what is the energy of 5? 5 has the energy, 5 is same as 1. Okay, so now this 7 is somewhere here, 6 is somewhere here, and 7 is same as 1. So 5, 6, when angle is 360, this is same as 1. So you will have this point. So 7 is same as 1. So now there is no point of rotating. We have got the 1 because so you see you have to draw this graph in a continuous way because conformation or angles are possible. Okay, this is called conformational analysis. So you can draw the conformational analysis potential energy diagram by adding the CS3 repulsion, CS3H repulsion, HH repulsion if this is given. If these values are not given, you can basically qualitatively you can plot this potential energy diagram because you know the CS3 repulsion is more than CS3H repulsion, and CS3 Gauche repulsion is less than CS3 eclipsing repulsion. If you know these things, you can plot the graph qualitatively easily. If the values are given, you can plot the graph quantitatively. That is the point. Okay, we will discuss in the next class.